Hello everyone. Today's session will focus on module number 7, which is Ethernet switching. After looking at module 4 and 5, the physical layer and the data link layer, one after the other, I think we're expecting to go for the network layer next. Right, someone just commented, you cannot see my screen. Anyone else who cannot see my screen before we continue? Are we good? Now I can. Thank you very much. Right. So, as I was saying, from the chapter number 4, we started looking at the layers of the OSI model, but we broke the sequence, the pattern here with module number 7, Ethernet switching. Why? Because it's a very crucial technology in networking. And since it belongs to layer 1 and layer 2, Ethernet switching is what we are going to be focusing on after what we did with the physical layer and the data link layer. Right, with we have what we call wireless LAN. So Ethernet, LAN, and wireless LAN, I think are two of the most prominent LAN technologies that are in use today. And starting with Ethernet switching, which gives us Ethernet LAN, we'll later on in CCNA 2 focus on wireless LAN. Ethernet LAN connections, all the cables that you see, Ethernet cables, copper cables, UTP cables, that sums up what the Ethernet LAN is. Wired connections. With wireless LAN, your Wi-Fi, your basic, what you call your Wi-Fi, that is the wireless LAN. So those two technologies are what makes up the bulk of the LAN technologies that we have in today's networking. Right, so today we focus on Ethernet switching mainly because it belongs to layer 1 and layer 2 of the OSI model. Module objective. The module objective is to explain how Ethernet works in a switched network. And we are going to be looking at explaining how the Ethernet sublayers are related to the frame fuse. We describe the Ethernet MAC address, explain how a switch builds its MAC address table and forward frames, describe switch forwarding methods, port settings, and port settings available on layer 2 switch ports. Right. Starting with switching, the word switching, the device switch. You need to understand what a switch is. A switch is a device, an intelligent device, which forwards frames. And when we are talking of frames, we are talking of data or information at layer number 2. So when we are talking Ethernet switching, it basically means we are talking of layer number 2 of the OSI model. That is where switching starts. Then with Ethernet, it extends to go to layer number 1, the physical layer, defining the standards of the cabling that we have, of the connectors that we have, and of the type of signaling that we have for transmitting our information. So I think if you can play around with the physical layer, the data link layer, you can easily define what Ethernet switching is, since it covers two of those layers. Right. Getting into our slides, starting with the Ethernet frames. Ethernet operates in the data link layer and the physical layer. It is a family of technologies defined by IEEE 802.2, 802. And 802.3. Right, 802.2, this defines the layer, LLC layer. Then from the MAC layer, going down up to the physical layer that defines the Ethernet, 802.3. Those are the standards that we have for the Ethernet. And Ethernet supports data bandwidth ranging from 10 megabytes per second up to 100 gig per second. And what differentiates these things is mostly the type of media that we are going to have. When we discussed the physical layer, the UTP cables, I think we went through different categories: Cat5, Cat6, Cat5e, Cat7, Cat8. Depending on the type of media that we are going to have, that will define the capacity that we are going to have for the network. So with Ethernet, we have capacities, bandwidths ranging from 10 megabytes to 100 megabytes. Right. At the data link layer, the Ethernet basically handles data framing. So at this layer, when we discuss the data link layer, what was the main function of the data link layer? The main function of the data link layer was framing, encapsulating information from the upper layer from the upper layers, all the protocols from the upper layers. We encapsulate all that information and we form a frame at layer number 2. So the same thing with Ethernet. Ethernet is a technology at layer number 2. That is where data framing is done. We also have media access control. With media access control, we defined collision detection, carrier sense multiple access collision detection, where if we have a shared network, if we had a shared network of which Ethernet, if in half duplex is a shared network, then there is need for algorithms which govern rules who should get access to the media. So at layer number 2, the Ethernet frame, at layer number 2, with Ethernet switching, that is where we have data framing, media access control, and we also have error detection there. So lastly, I just mentioned, let me see, data framing, right, media access control, then lastly, error detection. So Ethernet deals with these 3 at layer number 2 at the data link layer. Then since it extends to the physical layer, what does Ethernet is to do with the physical layer? In the physical layer, Ethernet defines the physical characteristics of the network. So with the physical characteristics of the network, at this layer, we have the cabling. What type of cabling are we going to have? What type of connectors are we going to be using? And lastly, what are the signaling methods that we are going to have? So Ethernet, I repeat, Ethernet, it belongs to 2 layers. As a standard, as a protocol, however you define it, it belongs to 2 layers, the data link layer and the physical layer. At the data link layer, it is responsible for Ethernet framing, media access control, and error detection. And at the physical layer, it defines the physical characteristics of the network. Right. Data link sublayers. The 802 line standards, including Ethernet, use 2 separate sublayers of the data link layer. We defined those when we did the previous module, which was the data link layer. You will see this module is a bit related to the data link layer and the physical layer. I already said the Ethernet belongs to 2 of those layers. So it will seem like we are repeating the same thing because Ethernet belongs to 2 of those layers. So we already defined the LLC sublayer and the MAC sublayer, with the LLC placing information in the frame to identify which network layer protocol is used for the frame. To simplify that, I mentioned something to do with translation. The LLC sublayer translates all the information that is coming from the upper layers, which is software. it translates uh, it translates all that information so that hardware understands all the software in the upper layers. So it's just an interface. The ALC is the interface between the software and the hardware. The MAC layer responsible for data encapsulation, media access control, and data link layer addressing. So the sub-layer, which is responsible for data framing, that's the MAC sub-layer. Right. Two of those sub-layers, we continue. The MAC sub-layer is responsible for data encapsulation and accessing the media. Data encapsulation, it includes the following with the Ethernet frame, Ethernet addressing, Ethernet error detection. That is basically what we have on IEEE 802.3 data encapsulation. When we see this, that defines Ethernet. That is the standard of the Ethernet, this IEEE 802.3. Right. So the Ethernet frame is the internal structure of this is the internal structure of the Ethernet frame. With the data link layer, we already defined the structure of the frame. I think it started with the start of the frame. Then we have the stop. At the end, we have the source, the destination, and the source MAC address. What else do we have? We have a component which is responsible for checking for errors. We have a component which is responsible for the payload that we have. We also have a component responsible for showing us the type of protocol that we are using in the network layer. I have someone in the chat. You can assist. Yes, the type. That is the type of protocol that we have in the network layer. We have the size. Okay. All right. So that was the frame. That was the general format structure of the frame. If you remember, we mentioned the data link layer. It translates all the information from the upper layers so that regardless of what is in these layers, regardless of what is in the physical layer. Right, let me get this straight. Regardless of what is in the physical layer, the type of media that we have, the type of environment that we're going to be sending our information, regardless of all that, all the information from the upper layers, they get to the data link layer, and the data link layer translates all that. Right. So at this layer, you might have Ethernet, where we define the physical cabling as, let's say, UTP. The type of media that we're going to use is copper. This is communication for LAN. Ethernet is for LAN. Right. This is one type of media, one type of environment that we can have. We can have, for example, a wide area network. From the data link layer to the physical layer, we can have a wide area network where we have protocols like point-to-point protocols taking off. The way the data in here is defined, it will be different depending on if we are using Ethernet or we're going to be using this point-to-point protocol or we're going to be using this protocol to define the physical characteristics uh, of our transmission. Right. So if it is different, here in this module, we start looking at Ethernet. If we have PPP, we have a frame which is different. If it is Ethernet, we have a frame which is different. If we have any other protocol, that frame will be different. Right. So with Ethernet, with the data link layer, what we did with the data link layer was just the general format that we have. That was the general format, the general structure of a frame. Here we are being more specific now. We are looking at the Ethernet frame. I'm putting emphasis on this because I've heard many questions. What is a data link frame? What is a frame? What is a data link frame? What is an Ethernet frame? What is the difference between them? An Ethernet frame is a data link frame, but it's a more specific frame because it's defining Ethernet at layer number 2, which translates up to the physical layer. So with the Ethernet frame, we also have Ethernet addressing. We also have Ethernet error detection. With the data link layer, we had all this, but it was just addressing. I think it was MAC addressing here. Then here it was just error detection. So that was general. Now we are focusing on specifics, starting with the Ethernet. Right, the MAC sublayer, media access. The IEEE 802.3 MAC sublayer includes the specifications of different Ethernet communication standards over various types of media, including copper and fiber. Legacy Ethernet using a bus topology or hubs is a shared half-duplex medium. Ethernet over a half-duplex medium uses a contention-based access method, carrier sense multiple access, collision detection. Ethernet LANs of today uses switches that operate in full duplex. And full duplex communication with Ethernet switches do not require access through CSMACD. Right, what are we looking at here? I think it's sort of repetition of what we've been saying. We have seen Ethernet evolving. Ethernet has evolved. How Ethernet started, it started here, the bus topology. With the bus topology, we have a shared medium. With a shared medium, it means we need to have algorithms like this one, right? So our networks have evolved from having this to now using switches, which are intelligent devices, which allows us to send and receive information simultaneously. So we have moved from half duplex shared mediums to full duplex, which highly improves the performance of the network, and basically that's it. So I think this is a summary of what we are seeing here, just the evolution of networks from half duplex shared medium, where we have a problem of collisions, where we need algorithms like collision detection algorithms, to now we are using a switch. A switch you can send is intelligent enough. You can send and receive information simultaneously with a switch. That wasn't the case when we started networking here with that bus topology. Even with the hub, that's a legacy device. I think you can still see it in some setups though. The hub is just a device where if I have, let's say this is A, let's have B, C, D. B, C, D. That's a hub. If I want to send information from PCA to PCB, what the hub does, it just broadcasts. It broadcasts everything, everything. It sends broadcasts. The problem with that, if A and B try to send information simultaneously, then we are going to have a collision. It is not intelligent enough to avoid those collisions. But with the switch, for example, the switch is intelligent enough to say A, B, C, D. If I want to send information from A to B, it does not need to broadcast because it uses MAC addresses. It can directly send its information to PC number B. That allows, with full duplex, with the combination with full duplex, it allows multiple devices to send information simultaneously. That's just the evolution of networks. Right. Ethernet frame fields. The minimum size of the frame is 64 bytes and the maximum is 1518 bytes. I just wrote a Huawei exam recently. This is one of the questions. What is the minimum size of the frame? What is the maximum size of the frame? You need those numbers to be stuck in your head. All those numbers. They might not seem necessary at this point, but they are very necessary. You need to know the minimum size is 64 bytes. The maximum is 1518. Why you need to know that? Because if you have a frame with the size of less than 60 bytes, that's a problem. We call that a rand frame, and it needs to be discarded. It needs to be discarded. If a frame is less than 64 bytes, it needs to be discarded. And if a frame is more than 1518, it's called a giant. It's called a giant. Here they call it a jumbo. And it needs to be dropped as well. So understanding these numbers, 64 and 1518 is very important. A question might come, we have a frame, 60 bytes. How is this frame going to be processed? Then you get your answers. It's going to be processed perfectly. It's going to be dropped. You need to know this is going to be discarded because it is a rand frame. Right. Now going to the frame views, you see they're almost the same as the general structure that we gave at the data link layer. With this one, we have 8 bytes of the preamble and SFD. The SFD defining what we call the start frame delimiter, which is used to synchronize between sender and receiver. Basically, this 8 bytes says this is the start of a new frame. This is the start of a new frame. If I remember very well, I think it's a series of 10s, 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 a continuous series of 10s, 10s. So if a device receives this information, it understands there is a frame which is coming, a new frame. If I go back a little bit, when we are communicating, what our devices here, what our devices here is just a series of numbers. 110101011101111. This is everything our devices are listening to. It's just a series of those numbers. So how do they know this is a frame, this is a new frame, this is a new message? How do they know that? With Ethernet frames, they know by these 8 bytes. These 8 bytes. So if there's a continuous of 10s, 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 8 bytes, they can count. If you have those numbers, it means this is the start of a new frame. Then from that, we know what is the destination mark. We know what is the source mark. We know what the type is. The type basically defines the layer 3 protocol that is being used, layer 3 protocol. And the most common that we use is IPv4 and IPv6. Then here with the data, this is the data which is encapsulated from the upper layers. Inclusive to that is our message in that data. Then the FCS that is used for error correction, error detection. We call that the frame check sequence field, used to detect errors in the frame. It has what we call the CRC. I think we're going to be looking at this later on. The CRC helps with detecting errors in the Ethernet frame. So another thing to note, you need to know all these components of the structure of the Ethernet frame is very important. Very important to know all those components. It's very easy actually. Very easy. Right. Let's go. Ethernet MAC address. What is a MAC address? We already defined it as the physical address, an address which is used to uniquely identify a device in a network. We have another unique identifier which we call the IP address. That is a logical address. You can see the difference that I've given to these two addresses. The MAC is the physical address. The IP is the logical address. Now, an Ethernet MAC consists of 48 bits as compared to the IP, which is 32 bits. You need to know numbers. This one, it has 48 bits expressed using 12 hexadecimal values. So with this one, those 32 bits, we express them using decimals so that we are able to see those numbers. That's why we see our 192s, 168, 10.10. This is a decimal number. This can be converted to 32 bits. Module number 5, number systems. I think that is basically what we did. Conversion of this to binary and conversion back to decimal. This was the IP address. Now with the hexadecimal, we have 48 bits which can be expressed as 12 hexadecimal values. Because a byte equal 8 bits, we can also say that a MAC address is 6 bytes in length. All right. 12 hexadecimal values. So what we have, we can have A, B, C, D, A, B, let me see, C, D, 0, 0, 0, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is an example of a MAC address, 12 hexadecimal values. This is what it's supposed to look like. I've just given an example. These are 12 hexadecimal values. We have ways which we can minimize that value. Hopefully we can look at those as we continue. All right, given that 8 bits, 1 byte is a common binary grouping binary of 8 zeros to 1 ones, can be represented in hexadecimal as the range of 00 to FF. So as we did with number systems, if you have a binary number like this one, how do you convert it to a hexadecimal? You group fours starting from the back. So if you group these fours, that's a 0. This is a 0. That's where this number is coming from. This is the hexadecimal equivalent of this. Then with ones, 4 ones, that's an F. The other 4 ones, that's an F. That is where the FF is coming from. When using hexadecimal, leading zeros are always displayed to complete a 8-bit representation. For example, the binary value of this is represented in hexadecimal 0A, right? With binary, what they are trying to say here, with binary, I can shorten this value to just 1010. It's still the same thing. I can remove these zeros, ignore, if I can say, those zeros, and have this value. And if I want to convert this to decimal, it's 8 plus 4 plus 2. This is 10. And if I want to convert this to decimal, it still remains 10. No problem. So I can ignore these zeros. It's not the same thing with the hexadecimal though. It's not the same thing with hexadecimal values. You don't have to ignore those values. So that's why we still have our 0 there. So the leading 0 are always displayed. They need to be displayed in hexadecimal. Hexadecimal numbers are often represented by a value preceded by 0x, e.g. 73. So a perfect example of this with let me go back. Let me go back to the type. If the type we have of the layer 3 protocol is IPv6, if the type is also IPv4, what's the value that is given in these 2 bytes? The value that is given with IPv, okay, let's say IPv4 here, let's say IPv6 here. The value that is given is 0x, it should be 800. It means it's 800 in hexadecimal. The value that is given for IPv6 is 0x 86 DD. Yeah, we should be correct. That's the value that is given for if you see this value in this type field, it means the upper layer protocol is IPv6. And if you see this value, it means it's IPv4. Of course, the devices will be seeing the binary values of it. But for demonstration purposes for us, these are the values that will be showing in hexadecimal. So what I'm just saying is if you see a value like this with the 0 and the x as the prefix, it means that value is a hexadecimal value. If you see as well a value that has an h at the end, it also means it's a hexadecimal value. So 73, let's put that in binary. Let's put that in hexadecimal. Help me. In binary, it should be 0, 1, 1, 1, 0, 0, 1, 1. Confirm if it's correct. That means in decimal, this value is 128.64 plus 32. Let me do some calculations. Going back to number systems. Okay, but where's my phone? Okay, let's do this. Can I make it? So it's 64. I'm very sorry for those who didn't pass through motion number 5. Plus 32 plus 16 plus 8, 4, 2, 1 plus 3. So that's 115. You can say it's incorrect in the chart if it is. So if we are given this decimal value, in binary, it's going to look like this. In hexadecimal, it's going to look like this. And the representation that you're going to see of this hexadecimal value is 0x73, or you can see 73H, or you can see 73 with the base 16. So these are three representations we can have of a number in base 16. It's very important getting this at this level. These numbers will just be popping up from everywhere. And now you'll be asking, what are those numbers? But they're very simple. It's just a number represented as a hexadecimal. Right. Ethernet MAC address. In an Ethernet LAN, every network device is connected to the same shared medium. MAC addressing provides a method for device identification at the data link layer of the OSI. Let that not be, I was wrong. For IPv4 and IPv6 representation, I didn't understand. Okay, so I'm saying, let's go back. What I was saying is, if, let's start with what you see, what the devices see, all these fields that are here. What our device see are numbers in binary, ones and zeros, ones and zeros. So it will be seeing 8 bytes, 8 bytes, that's 8 times 8, that's 64 bits. So in this, I'm explaining from 0 so that we get where these numbers are coming from, right? So these 8 bits, these are just 64 bits. So these are 64 one zeros, one zeros, one zeros, one zeros. That makes up the frame. Here we have 6 times 8, 48 one zeros, 48 one zeros, which define the destination MAC, which define the source MAC. Here we have 2 bytes. 2 times 8, that's 16 bits. Those 16 bits define the type of protocol which was used at layer number 3. Why is that important? It defines the type of protocol at layer number 3. And the type of protocol we have at layer number 3, it can be IPv4, IPv6. Those are the major ones that we use. We can have ARP as well, but let's discuss these ones. So if the type of protocol that we're using in layer 3 is IPv4, what the device will see in this field here, it will see a number like this one. This one is in hexadecimal. Basically, that's what we are saying. If it is IPv6, this is the number that will be here. So for example, if I take 866DD, let's take this one. I think it's much easier to explain. 866DD. How many bits are these? These are 4, 8, 12, 16, which are equal to 2 bytes. So what will be in this field will be 8. What is 8? 8 is 100, right? 1000. 6 is 0, 1, 10. Then D is 10 is A, 11 B, 12 C, 13 D, 13 1, 12 0 1, 1 1 0 1. This is the binary value. So if our device sees a value like this at this field, what it basically means is the upper layer protocol which was used is IPv6. Are you getting anything, Don? Are you getting anything?
Yeah, I
And
get it now. Get it.
are you getting now? Yeah. And the reason why I just introduced these numbers was to demonstrate the representation that you will see with the text that we're going to get in all the modules that we're going to be doing after. You're going to be seeing these numbers a lot. So I just introduced them so just you understand where they are coming from. It's just a representation of a hexadecimal value. All right. Ethernet MAC, all MAC addresses must be unique to the Ethernet device or Ethernet interface. To ensure this, vendors that sell Ethernet devices must register with IEEE to obtain a unique 6 hexadecimal code called the OUI, organizationally unique identifier. An Ethernet MAC address consists of 6 hexadecimal vendor OUI code followed by 6 hexadecimal vendor assigned value. All right. So what we have here is the structure of the MAC address. Right. I'm seeing a minute left there. Let me continue from where I just left, defining the structure of the MAC address itself with the OUI on one side and the vendor assigned value on the other side. You know the deal. Join in soon after.